Thank you very much. Thank you. Appreciate it. Thank you very much. I hope you can hear me all right, and I'll start. Yes, I'll be talking about Liutex identification of coherent structure in turbulent two-phase flow. I would like to acknowledge my colleagues, Dr. Farid Rusta, Dr. Bamdal Lassani, and Dr. Lu. And I'll be presenting, but the work is done by all the group. So I'll be going through a quick outline of gas-solid flows and talking about Euler and Lagrangian approach and governing equation. This is DNS simulation, so I'll talk about that. Also, we have done some one-way coupling and two-way coupling analysis. By that means that one-way means the flow essentially carries the particle, but particles do not affect the flow. The two-way coupling, which is we also looked at the Liutex identification, is the coupled two ways, and particle affect the flow as well as the flow affecting the particle. I'm gonna show some sample, simulation result for two-phase flow, and then talk about particle concentration, particle deposition in turbulence, and then look at the vortex identification for two-phase and talk about their effect on the near-wall coherent structure and particle transport, and also look at the effect of influence of particle Stokes number and conclude. There are numerous applications for particle-laden flows, which are samples are shown here from, respiratory transport of aerosol, transmission of, diseases by viruses, etc., droplets which are emitted by through mouth. Sediment transport is another big area. Blood flow is another major area that flow is significantly two-phase with 40% hematocrit. Air pollution is another potential application of two-phase flow. Volcanic activity and eruption is another one. Even rain formation in cloud is actually a two-phase flow combination. Also, sand and dust transform are examples of two-phase flows. I'll here mention that, the reduced fluid regimes at, this is essentially shows the effect of mass loading and volume fraction of, second phase. For very small mass loading and small volume fraction, one-way coupling can be used. That means the particles are small, the volume fraction is small, and therefore the flow essentially carries the particle, but the effect of particle on the flow is negligible. But as the mass loading increases, then the flow becomes two-way coupling. That means at a very high concentration, the particle also affect the flow, affect the turbulence and modifies the turbulence. And if volume fraction is also high, in that range, actually flow becomes four-way coupling, meaning that the particle and flow interact and exert force. Also, the collision between particles become important, has to be included in the analysis. So the objective for this presentation is we want to have a better understanding of turbulence near wall flow structures and how they affect the particle, examine the effect of particle Stokes number on particle deposition and concentration variation, assess the importance of Liutex identification on the near wall turbulent flow structure, and also evaluate the Liutex in particle laden flows and assess their effect on accumulation and the concentration in the low speed streaks. These are just various approaches that we use to analyze flows basically, and the DNS resolve all the details, essentially all the scales of the turbulence and everything, and the sample jet flow shown in here on the DNS analysis. RANS is on the right side. Things are averaged, over a space or time, and then this gives a kind of a smooth variation of the mean flow, but does not resolve many of the smaller scales. LES is actually between the two. We essentially filter the high frequency and capture the whatever frequency we can analyze with the because the DNS cost a lot. Computation is very extensive because to resolve all the scale of turbulence down to Kolmogorov. LES you resolve as much as you can, and then you model the subgrid scale basically. This is just a, a direct numerical simulation approach here. The code we are using is a spectral code. The equation are written down here, and if there is a two-way coupling, then the source term also is shown in the on the Navier-Stokes equation. Everything written in vol unit in this case, and that's the. And the method is a spectral. I'm not going to go through the detail, but basically we expand, the velocity field in a kind of Fourier series in x and z direction. In the y direction is Chebyshev polynomial to satisfy the boundary condition. Is for a channel flow, basically only application. And this is the geometry we are simulating. Is about 630 vol units in x and z direction, and about 250 half a channel 125 in vol units in the y direction. The velocity at the upper and lower wall are zero basically, and it's periodic in the other two directions. And we have run it also for larger sizes, but that size resolves most of the range we want. This is a sample simulation. This is a cross section of the flow. Flow is toward essentially the wall here, toward the perpendicular to the screen, and you can see the eddies form in turbulent flow, mostly near the wall. They interact and form and change, and these are essentially resolved by this scheme. It's a quick kind of, at least simplified validation. The streamwise velocity as predicted by simulation and compared to the law of the wall, it seems to do pretty well with validation. For the particle, we are using, the equation of motion of the particle. Newton's law is mass time acceleration equal to all the forces. The forces are drag force, lift force, Brownian force if this particle is nanometer range, and gravity, and all of these affect essentially the motion of each particle, and and of course the particle could also affect the flow, as I mentioned before. These are in vol units. I just wrote the unit here in the bottom, and the drag coefficient here also is written here, and an approximation for different range of Reynolds number. These are some, we want to look at here how the particle on the average move. This is again channel flow. You can see that the fluid is in black. The black line is fluid, and then for different, essentially particles with different relaxation time are written here. 10 to the minus 4 are very small. Essentially follows the the fluid basically. As you go to a tau plus of 40, which is the dotted line, we can see that the flow, actually the particle near the wall kind of, is larger than the fluid velocity. And the reason is because the particle moved toward the wall from, further away, has higher velocity, and because of inertia, they maintain some of it. So, and these are written for a range from, from 10 to the minus 4 to 40 range. And this is the U prime fluctuation, root mean square velocity, rhin here basically, versus y plus. Again, we see, of course, at the wall, everything is zero, and but the particle velocity close to the wall fluctuation is larger than the fluid. And the reason is because the particle come from further away toward the wall, basically. And we can see that it increases as the particle relaxation time increases, the amount of root mean square fluctuation increases, basically here. Same here are shown for fluctuation in the V prime direction, in the vertical to the wall direction, that we see here, away from the wall, the particle velocity is less than fluid, the fluctuation, but close to the wall, the fluctuation of the particle is larger than the fluid fluctuation. Less than about 10 or 9 vol units closer to the wall. The W prime is actually always less than the fluid, basically, in that direction. And these are the turbophoresis effect. There's a net flux of the particle toward the wall. Again, we see that the larger particle with larger tau has the larger mean flux toward the wall on the average, basically. And we also looked at various other, other kind of, correlation. This is the fluid particle velocity correlation. And for three different cases here, lycopodium particle, which are kind of light, they're 28 micron here, density is 826, glass particle, diameter 50, density 2000 more, and then copper, which is 70 micron, and of course the density ratio, this density to the flow, to the gas here, the fluid is air, is 7,300 basically. So it's, we see that, of course, and then these are compared for three different directions. We have analyzed here upward, no gravity, and downward, and these are different colors shown here. And we compared with the earlier studies of Wang and Squirrel, which is downward flow, and it seems to, at least the simulation, are comparable. Also, to understand the particle behavior close to the wall, we did some kind of a simulation, which is shown in at time zero, the particle are very close to the wall. Everything is started at 5 wall units from the wall. And then we look at how time goes on, how they move away from the wall. I mean, one would expect possibly that it's a diffusion process, so it's randomly going, but we can see, look at the time 100 and 200 seconds. It seems that it's not, well, it's random, but it's not completely random. It seems that there are a spike at different regions. And these are because of the coherent structure near the wall, that there are counter-rotating vortices. There are regions that the particle and the flow is shoot up from the wall, and some region is essentially moved toward the wall. And this here, in this case, those kind of high peak are because of the particle, the flow being expelled from the wall and carries the small particle, basically your 10 micron here with it. And this is sort of also another, kind of simulation verifying that. This is the upper wall here, and we are looking at the, at the contours of essentially, fluctuation velocity in the vertical direction. And then the upper wall is the wall here. We are within about 20, 30 wall units close to the wall, and we can see that the periodic kind of flow upward and downward. This is actually averaged. Velocity is averaged over 50 time steps. Otherwise, it's pretty random. It's very hard to see. But averaging over this, we see in some region the flow goes toward the wall, and some region goes away. Is roughly periodic, with a period of about 100 wall units, actually, which is consistent with what we know about the particle pattern. And here is the deposition pattern. When we did this simulation, I was like expecting to see a random kind of deposition, but the particle actually seems to, essentially deposit on lines approximately. Of course, it's random, but you can certainly distinguish the lines at different, location that the particle. These are the region that counter-rotating vortices goes toward the wall. Essentially suck the particle toward the wall, and because of inertia, these are 25 micron, they hit the wall, and essentially because of van der Waals, they get deposited. And of course, this is, again, if we go over a long, because these, coherent structure also rearrange themselves varies randomly at long time, everything become kind of uniform deposition. But for a short time duration that, these coherent vortices control the deposition process, and they're essentially linear kind of deposition and linear kind of flow leaving away from the wall. This schematic shows what I'm talking about. These are counter-rotating vortices here, which are about 100 wall in period. The radius, if each one is 25 wall unit, you can see that in this region, don't know if you can see my slide, but anyway, flow is outward leaving, and then in the next one is downward, and then upward again. And these are approximately, about 100 wall units apart. Basically, the total period is 100 wall unit. Each, each of these are the radius of each of these kind of cylindrical shape is 25 wall units. We also did simulation for one-way coupled and and four-way coupled here with different mass loading. The first one, essentially, mass loading is very small. The particle do not affect the flow, and this shows most of the you can see the turbulent dynamic is the strongest in that case. As we increase the mass loading, the particle interact with the flow and essentially damp turbulence, depending on the sizes, of course. But for 20%, you can see that the amount of vortices just by eyeballing it is less. And then by 40% mass loading, even less. So the two-way coupling, for large particle, at least damps the turbulence basically on the whole. And these are, again, root mean square velocity for one-way couple and two-way and three-way couple, four-way couples. And we can see that sort of, as you go to, 40%, particle, but mass loading, it stamps the particle more generally. And, so as increasing the mass loading decreases the particle fluctuation. And then there are some structure formed by the particles which are known experimentally. This is some of the data of Fessler from 1994, actually. And he tested, some 70 micron copper particles. And for this range, basically, the distribution of the particle in the center of the channel is roughly randomly distributed. You can see the experiment on the right and our simulation on the left. As you go, basically this is for 50 micron glass particle. Again, there is still more or less random, but when we go with leucopodium here, 28 micron leucopodium particle, you can see experimentally they form a structure. That's because of the interaction of these particles with the vortices in turbulent flow and and the vortex formation and etc. That essentially causes the particle to essentially centrifugal force pushes the particle away from the vortex, and they essentially get gathered on small lines, as you can see. And again, the simulation here and the experiment seems to at least qualitatively agree. As we go, this is again for the simulation done for tau plus of 10 to the minus 4, which is completely random. This is the center of the channel or near the center. And then at tau plus of 1, there is some structure begin to form. At 4, you can see them more clearly. And then at 10 and 20 or, and 10 at least seems to be most interaction happens and it's very clearly seen. As you go to 20, it damps a little. At 40, it damps more. If you go to higher, then it can become random. So for a certain size class, essentially the interaction becoming very strong, and it formed this structure. I mean, actually, this is one reason we have rain, in fact, because there was a puzzle in the past that particle in the cloud are, the amount of droplets are so small and size are so little that the chance they collide and become rain is small. But because of turbulence in the cloud, they apparently concentrated on these lines around this pattern, and concentration is high enough that they can collide and become rain. So turbulence in this case help us to have rain. This simulation here basically is one-way coupled. If you do with higher, the amount of fluctuation become less. This is another picture, of a snapshot for 10 micron. And here we put in the vorticity fluctuation also on that picture. Basically, you can see that the location that there are high vorticity and probably vortex formation in those, essentially they're empty. And the particle are moved to the boundaries between these vortexes or high vorticity region. It's a little movie here. I don't know if it works. So this is a uniform concentration. You can see the starts. And this is again for 10 micron that the structure form. You can see gradually, this is a DNS simulation at the mid section of the channel, essentially forms those structures, because of turbulence interaction with the particles, basically. And also, if you're close to the wall, the pattern changes, and we already know more about that. Actually, we have done the same simulation with larger domain, just to make sure it's not because of the domain effect. And you can see again, the structure form. This is twice the size of the periodic cell we studied earlier. This is 1200 by 630 by 630. And you can see again the wall, and then the red spot, which are high vorticity or high vortex level ratio, is the sort of center of rotation, and centrifugal force pushes the particles away. This is basically the same, but in the wall region. You can see the pattern changes now. If you're close to the wall, you generate those coherent structure, and you have high speed streak and low speed streak. High speed is the region that particle flow moves from the wall toward the center. So velocity is slow. It's referred to as low speed streak. And then the other one is essentially flow goes from the top at higher velocity toward the bottom, so become high speed streak. And you can see this pattern here, and the distance between them is roughly about periodic cell is about 100 wall units. And the concentration, the way it changes is shown in here. For one-way couple, we can see, there is a, this is for top loss of 800, so it's quite large, but, the maximum concentration very close to the wall goes very high. And if you do it, basically, four-way coupled and, also at 20% and 40% and then 100 and 200%, basically we went to all the range, and you can see that there's a higher concentration, and the amount of shift toward the wall becomes smaller because essentially the turbulence intensity decreases with the four-way coupled analysis. And we have done this, again, the structural pattern, for 40%, mass loading. And you can see that basically, one-way couple is the strongest situation as you go to higher loading, and then we did different tests. The one on the top left is one-way couple. On the other three are essentially, for mass loading of 40%. And the right top is actually only collision. Collision between the particle was accounted for, but the coupling, were not. In the lower left is two-way couple. So in this case, the flow interaction is accounted for between particle and the flow, but the collision was neglected. Four-way couple has both of them, both two-way coupling of fluid particle and also the particle collision also included. Particle collision essentially smears things up a little because it just increases randomness. But it's still for this size of top loss of 20, the structure can be seen in the middle of the channel. And this is basically, again, it is at y plus equal to 10, and this is 40% and 20. Again, we made this comparison. You can see the flow structure near the wall, which was, elongated, kind of, shape in this form. In one way is the strongest, you can see it, and then pure collision make this smeared somewhat. And two-way coupling also smears a little bit, and four-way coupling also smears a little bit, but because of collision, it's a little more random than the one-way coupled. Okay, so for two-way coupling, I'll just summarize quickly what we are doing here. In this case, Navier-Stokes equation has a forcing function because force of the particle acting on the fluid, and the particle essentially, of course, the same equation we had as before, and this is basically, and in this part of simulation for Liutex identification, we just use two-way coupling basically. And and the computational domain in this case is slightly different from the other cases I showed here. DNS essentially had a 128 by 128 by 128 essentially cube. The domain was essentially 2 pi h by 2h by pi h basically, and Reynolds number based on shear velocity is 180, which is a fully turbulent condition basically. And we did, different cases, the flow, upward or downward, gravity in the direction of flow or opposing the flow. And we also here use the Stokes number, which is very similar to relaxation time, but non-dimensionalized ratio of the particle relaxation time to fluid time scale. And then here, again, we are, here comparing our results with Marchioli's results simulation of 2008, just to make sure things are working okay. These are particle velocities and compared with his work. And we see that, for Stokes number of 1, 5, 25, they are following the same trend approximately, and they're probably, and then root mean square velocity of the particles also is comparable to Marchioli's earlier work. So that sort of at least verifies partially our result. We also did a Liutex, evaluation here. These are the contours of, a magnitude of the Liutex here for different particle Stokes numbers. In this case, we use the fixed number of particle, about 200,000 at different sizes to generate various Stokes numbers. So when the Stokes number increases, the mass loading also increases because the total number was fixed. So there's, to interpret them, we have to follow that idea also. And then this is for two is kind of close to to the one-way coupled, and you can see the structure of the of the Liutex, very close to the wall, in this case, less than 10 wall units away. And these are, the velocity was average in a non-dimensional time of about 0.1, and then we evaluated the magnitude of the strength of the Liutex, the absolute value of R here. And then for 10, you can see that is some decrease, but it's still actually is an increase in 10, is more interaction. It seems to be the structure is somewhat increases, but 50 decreases, and 100 of course decreases a lot more basically. And this shows an average Liutex strength average here, across the, for a large time duration of about 10. So you can see that, the vortex at Stokes number of 2 is relatively large. I mean, the peak is, of the order of probably 20 to 25 range. You have the peak, and at the wall, of course, is 0 and increases with magnitude there. When you go to 10, actually, it increases somewhat more. The blue line is slightly more than 2. But then when you go to 50, it decreases, the green line, and then for 100, decreases even more so, as we mentioned in this case, because the mass concentration increases, that essentially damps the turbulence, and also the strength of the vortex decreases. This shows, again, the vortex essentially with the vector. I mean, the contours are the strength of the, the Liutex, and the direction is the direction of the Liutex vector here. And you can see that, in some part they are along the flow basically, and the other side is opposing it. We sort of interpret that very close to the wall there are coherent vortices which are counter-rotating. So in some region they rotate in one way, and the other region they return the opposite way. So for s equal to 2, you can see that more clearly. Also for 10, you can see them again more clearly what's going on. As you go to the higher value of Stokes number, the intensity decreases basically, and and that's sort of shows this picture. This is actually interaction with the essentially we are showing the velocity field, the Liutex strength, and the particle concentration at the same time. For s equal to 10 is the first top row kind of, and excuse me. You can see as you away from at the wall, of course, velocity is 0, goes kind of dark. Away, I mean, the scales are on the top also shown for the strength of the vortex lines, which essentially we made the contour lines for the intensity of the vortex, and the velocity in the x direction essentially is contour with velocity magnitude kind of. So you can see that the top is red, and toward the bottom, of course, goes to 0, become blue and dark finally. And then the vortices are also here estimated as shown, and you can see that there are the yellow is a high level of vortex strengths, and there are several of them, and we sort of enlarged the couple of them for in the top row. The right one is the enlargement of that section which is shown. In the bottom, which is for s equal to 100, again, we enlarged the small section of the flow on the right, and you can see how the vortices strength and how the particle tried to move away from the wall in those regions. So there is seems to be quite a bit of interaction between particle and vortices, and that would be probably an interesting area for further research, certainly. So anyway, so basically these are, as I said, the vortex or isolines, which are yellow is sort of the highest, kind of level contours, and toward as it decreases, I mean, of course, it goes to blue and later smaller. We also actually looked at particle kind of concentration close to the wall, essentially plotting here very close to the wall within the distance of by plus less than 10. We are looking at the concentration of particles in that region. For s equal to for the Stokes number of 2, almost 17.6% of the total number of particles are in this region. So a lot of migration from the core toward the wall. And they are also lining up, as you can see that some region they are higher, some region they are less. Then the low speed streak region, there seems to be a good concentration of the particle. When S is equal to 10, actually the migration increases quite a bit. More than 60% are in this region. And then, you can see the lines also become much thicker. So there's a lot more particle in the low speed streak. As you go to 50, then, it becomes a little somewhat diluted, but still quite a bit of concentration. At 100, concentration, the total migration decreases, but still in the, in the low speed streak region, there is quite a bit of particle, kind of moving in that area. This is almost the last picture I'm going to show. So this shows the particle concentration for different Stokes number on the average, versus distance from the wall. And you can see for Stokes number of 2, there's quite a bit of particle close to the wall. Actually for 10 is the largest. For 2 actually is black, which is down there, is actually close to red, is under the red. So they're not that much. As we've seen, for 10 is the highest peak basically, and then 50 is still large, and then for 100 it goes down to become almost the same as 2 more or less. So that shows the concentration near the wall. We are also very interested to know the deposition rate on the wall for a small particle. That's very important in many industries. And the graph here shown, non-dimensional deposition velocity versus Stokes number. And you can see that, as the Stokes number increases, of course, we didn't go to the smaller range. If you go to a smaller range, Brownian motion will cause further increase up. So it's a U shape. So this is just the leg of the U, which is increasing. But that's very surprising that how it happens, because diffusion process, as particles become bigger, the intensity decreases, the position should decrease, which happens in laminar flow. But when flow is turbulence, the interaction of particles with the turbulent vortices essentially increases the deposition. And essentially it shows that this, the graph is increasing. The small circles are experimental data collected by a large number of people over the course of time. The other simulation, DNS one by us and many others, are also plotted here. And the current kind of analysis is the blue line, which shows that it is consistent in that range. I mean, some of the experimental data has surface roughness, which increases. Here we are assuming idealized, completely smooth surface. So we're getting the lower bound of essentially the data here. And also we looked at particle normal velocity toward the wall, basically in the V prime direction, and this is versus Y plus. And you can see that, 100 essentially has the highest kind of velocity. And then as you go toward the smaller size, that decreases. Near the core, it sort of changes, kind of some direction. But anyway, that's the way it varies. So that gives a, so to conclude, basically, turbulent near wall structure and particle Stokes number play an important role on particle deposition and concentration profile. Presence of a small particle attenuates the intensity of turbulence fluctuation. A two-way coupling decreases the particle deposition. I didn't show the data, but that's also, you can find it in papers. Liutex identification provides much better understanding of physics of near wall turbulent flow structure. A maximum Liutex strength in our case is seen for ST of about Stokes number of about 2, and then for Liutex identification shows that particle accumulated in the low speed streak. This is sort of basically a preliminary work. We hope to continue this work in future, applies the identification to better kind of characterize the physics of near wall particle flows, and then use this to develop a model for interaction of the particle with turbulence. I mean, that interaction we saw it in some of the simulation is very strong and generate this very interesting structure near the wall as well as in the core of the domain. And then finally develop a Liutex-based subgrid scale model for LES of two-phase flow. There was a large number of good, really very good papers on using Liutex for subgrid scale modeling of the flow, but interaction with turbulence is another phase which is really important and need to be studied. But that's our for future work. And thank you very much. And I'll give you this little picture here as the shows that the flow velocity is in green and Liutex formation are also shown. The vectors on the Liutex are actually the Liutex vector, but the contours are Liutex strengths basically here. That's for Stokes number of 2. Thank you very much. I'll be happy to answer any question.